Have you ever really thought about why the ocean is salty? You know, it's one of those questions you might ask as a kid, but the answer? Wow, it uncovers this incredible story about our entire planet, its geology, its chemistry, and even its climate. So, let's dive right in. First things first, just how salty are we talking? Well, on average, about 3.5% of the weight of any bucket of seawater comes from dissolved salts. To put that in perspective, if you could somehow evaporate all the water from the oceans, you'd be left with a layer of pure salt about 180 feet thick covering the entire planet. That is a mind-boggling amount of salt. Okay, so where did it all come from? I mean, it wasn't just there from the start. The real story is how the planet has been slowly, very slowly, seasoning its own oceans for billions of years, and it happens in two main ways. Our first source is the land itself. Yeah, for hundreds of millions of years, the continents have basically been dissolving into the sea, bit by tiny bit. It's this constant three-step journey. It starts with rain. Rainwater is naturally a little bit acidic, and when it falls on land, it wears away at the rocks. This process, called chemical weathering, breaks the rock down and releases all these dissolved ions, which really is just the scientific term for salts. Then, you have all the streams and rivers acting like a massive global delivery service, carrying these ions from deep inland all the way out to the ocean. Now, the second source is way more dramatic. This one comes from deep inside the Earth. All over the ocean floor, seawater seeps down into cracks where it gets superheated by magma. This hot, mineral-packed water then shoots back up into the ocean through what we call hydrothermal vents. You can also add in underwater volcanoes erupting and giant underground salt domes dissolving, and you've got this huge infusion of minerals coming straight from the planet's core. So what exactly is all this salt? I mean, seawater's got a lot of different stuff dissolved in it, but check this out. Just two ions make up about 85% of everything, and those are chloride and sodium. You probably know them better as table salt. That's right. The vast oceans are basically seasoned with the same stuff that's in your salt shaker. Okay, and this is where it gets really interesting, because all this salt is constantly pouring into the ocean, but the ocean's saltiness doesn't seem to be changing, and that presents us with a fascinating scientific puzzle. In fact, scientists have found that the ocean's overall salinity has been unbelievably stable for more than 100 million years. It's reached what they call a steady state. This stability is so reliable, it's actually a scientific law, the principle of constancy of composition. It basically means that whether you take a sample of water from the Arctic or the Pacific, the ratio of the major salts to each other is always the same. The recipe is constant. Which brings us right to the core of this paradox. If rivers are dumping an estimated 4 times billion tons of dissolved salts into the ocean every single year, why on earth isn't it getting saltier and saltier over time? Where is all that salt going? Well, the answer is that the ocean isn't just a big bucket collecting salt. It's an incredibly complex, dynamic system. Think of it like a bank account with a perfectly balanced budget. There are deposits, sure, but there are also withdrawals. This diagram shows it perfectly. On one side, you've got all the inputs, the salt coming in from rivers and vents. But on the other side, you have outputs, processes that are constantly removing salt from the water. In this enormous chemical budget, the amount of salt coming in is almost perfectly balanced by the amount going out. So what are these salt drains? Well, there are a few big ones. A major one is a process called reverse weathering, where ions in the water are used to form new clay minerals on the seafloor. Other ions just get buried deep in ocean sediments, locked away from millions of years. And of course, marine life, from tiny plankton to corals, pulls ions out of the water to build their shells and their bodies. It's this slow, patient, planetary balancing act. So, the overall saltiness of the ocean is stable, but that definitely doesn't mean it's the same everywhere you go. If you look at a map, the ocean's surface has these big patches that are saltier or fresher than others, and there's a really clear reason why. Now, this is so cool. Take a look at these two maps. The one on the left shows where evaporation is highest versus where rainfall is highest. The one on the right shows sea surface salinity. See the resemblance? The patterns are almost identical. It's not a coincidence. It really comes down to a simple relationship. Anything that adds fresh water to the ocean, like rain, rivers, or melting ice, is going to make it less salty. And anything that removes fresh water, like evaporation or sea ice forming, which pushes the salt out, is going to make it more salty.
That's exactly why the subtropics, with all their sunshine and high evaporation, are the saltiest parts of the open ocean.
Okay, so why do we care about these subtle differences in saltiness? Well, it turns out that salt is an absolutely critical ingredient in the engine that drives our entire global climate.
Here is the key. The density of seawater, how heavy a gallon of it is controlled by just two main things: its temperature and its salinity. The rule is simple. Colder water is denser, and saltier water is denser. And what does dense water do? It sinks. This sinking action is the engine for what scientists call the thermohaline circulation. You can think of it as a massive global conveyor belt of deep ocean currents. In places like the North Atlantic, the surface water gets really cold and really salty, making it so dense that it sinks all the way to the bottom of the ocean. This pulls warmer surface water in behind it to take its place. And here's the crucial part. This conveyor belt is constantly moving heat around the globe, carrying warmth from the equator up toward the poles. Without it, the tropics would be way hotter, and places like Northern Europe would be much, much colder. So salinity is a key lever in the machine that regulates our planet's climate.
And that brings us to a final, really important question for right now. As the polar ice caps melt, they're pouring huge amounts of fresh water into the ocean, especially in key spots like the North Atlantic. If that fresh water makes the surface water less salty and therefore less dense, what happens if it stops sinking? How could that alter the ocean's conveyor belt, and what might that mean for our global climate? It's just a powerful reminder that something as simple as the salt in the sea is deeply connected to the future of our world.